Welcome to AP Podcast 10.2. We're going to spend time with liquids, solids, and how those intermolecular forces work with those two phases of matter. First of all, with liquids, they are definitely, the properties are due to the internal attraction of the atoms. So if you think about just liquids in everyday life, here's beading, for example, and everyone has seen beading. Imagine a surface, whether it's a car that's been freshly waxed or a deck that has been freshly finished, and you see water on it. You see these beads of water. It's kind of neat to see. And what's going on in there is some surface tension happening a little bit, but all those intermolecular forces are attracting the water to itself and causing that beading effect. Surface tension, probably your best example of that is a graduated cylinder and the good old meniscus. And what's going on there is that the surface is attracting the water, because water is polar, and the glass tends to be polar, and so it's sticking to the side. So that's why we get a meniscus. Capillary action, you may have seen it before, but if I were to have a little vat of water, and I were to stick this teeny tiny capillary tube, the water would go up that tube. The only real example I could think of that is sometimes in the doctor's office, they'll prick your finger and then they'll put a tube there, and the liquid will go right up the tube, kind of magically. But again, that's due to the internal attraction of the atoms. So as far as liquids go, if you've got stronger forces, those would increase. All right. Continuing on with liquids. Now the thing is, you can't see the molecules, so we want to picture them a lot like gases, where they're flowing, but they're attracted to each other by those intermolecular forces. And so as far as the molecules being stacked and so on like solids, you could think of it a little bit like that, but as you guys know from our chapter on entropy, there's more disorder. Okay, and then as far as comparing them to a gas, well, in gas particles we're talking about them far apart, right? Where liquids, they're closer together, but there's some kind of flow. So that's our model for the liquids. That's how we think of liquids. Now for phase changes for solids, liquids, and gases, it's really dependent upon three things. We've already talked about the intermolecular forces, how that affects whether something is a solid, liquid, or a gas. But this one's very obvious to you. The temperature is involved. And you can imagine you've got a block of ice, and then you add some heat, right? And what do you get? You get water flowing, right? You get liquid. So temperature plays a big role in phase changes. And then something that's not as obvious to you right now is pressure. But pressure definitely plays a role in phase changes, and we'll get to that when we start talking about phase diagrams, melting points, and boiling points. All right, let's move on to solids. Now, solids, there are two major types, and there's the kind that we're very familiar with, and that's the crystalline solid. If you think about all the powders that we looked at last year when we were doing chemistry, all those powders, for the most part, were crystalline solids. They were locked in some kind of lattice. If we could see on a level that was microscopic, we would see that there are things, they're in some kind of, well, I can't make that dot. There was some kind of locked in lattice work, and after a while you just get this repeating pattern and over and over and over. So that's the kind of solids that we're used to. The other kind that we're not used to, or I guess that we don't pay attention to too much, is amorphous solids, and those are said to be frozen in place like glass and plastic. Now, I have heard that with glass, if you go to some old homes, like homes that were around with the settlers, you can see at the bottom of a window pane that the glass down here, this bottom area, is actually thicker. And the reason for that is gravity's pushing down, and the glass is slowly flowing. Not something I've really witnessed, but I've heard it enough times where I tend to believe that. Right? So we've got those. That's our solids. We've done liquids. We've talked about intermolecular forces. What about metals? What about a chunk of iron? How in the world does that stay together? Well, let's talk about the bonding model for metals. If you think about it, you've all seen an aluminum can or a piece of steel or maybe a ball bearing, something like that. And those are not molecules that are bonded together. There's not covalent bonds. There's not ionic bonds. How in the world are they sticking together? Well, we have a model for it, and in AP, the model that we're going to focus on is the electron C model. Oops. And that's where we just think of all the atoms, all the metallic atoms kind of stuck together, sharing their electrons in a sea of electrons, so to speak. The other model, the molecular orbital model, is something that is a little beyond the scope of this class, and those of you that take a little more advanced chemistry will be looking at those. So as far as a diagram for electron C model, imagine this is my piece of metal, whether it's gold, silver, aluminum, whatever, and you've got the nuclei. Now obviously these are not in shape, but you've got the nuclei here, and those are positive, and the electrons are all floating around it. Imagine electrons, 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 okay? And they're basically sharing their valence electrons. And so what's nice about this is if I add a wire here and I pump electricity in, right? And I pump it in, and I have a wire over here, because these electrons are kind of free floating, they're not really locked into the metal, they can flow out. And so that's the model we use for metals, a sea of electron models. This also allows metals to be molded. Ductile and malleable and that kind of thing. It all has to do with the way these metals are. So that's the model we're going to hold for metals. So we've got those solids, those metals, we've got liquids, and now we got to talk about a special kind of solid, and this is involving the element carbon and silicon. Alright, for these two elements, they make up a network atomic solid. And you know about diamond, you know about graphite, but what we can do is we can view these as giant molecules. And it gives them some special properties that are pretty unique. Both carbon and silicon are brittle. They don't conduct heat or electricity very well. Carbon, I don't know what that is. Graphite and diamond ceramic, those are the kind of types there. Now, diamond is the hardest substance known to man. Graphite's slippery and it conducts electricity. Let's look at a model of diamond. Now, when I said diamond and silicon, you can imagine that that these could all be silicon atoms. Because if you think about it, silicon and carbon are in the same row, right? So these could all be silicon atoms. But anyways, they're connected in a nice tetrahedron, bonded to 4 other carbons or silicon in an sp3 hybridization. And this locking in this tetrahedral shape makes this super, super strong. And these sigma bonds right here give this molecule a distinct hardness. Now, graphite's a little different, though. Graphite is bonded in 3 places with sp2 hybridization. And so what this means is that with graphite, you've got these levels. There's layers. You've got this layer up here, and you've got this layer up here, and the pi bonds are above and below the plane. And so what that does is that allows carbon to go ahead and conduct electricity along this plane, which is kind of interesting. So you could pump electricity in there, and graphite will conduct electricity a little bit. But this is not a hard substance. In fact, it's super slippery. And the reason it's slippery is because these layers will slide right past one another. All right? But to get back to the covalent network solid, this is really, really the strongest bonding there is. In fact, this is, I would go so far as saying this is stronger. Oops, not that one, pardon me. Those of you that are catching my mistakes, I appreciate it. This one right here is stronger than ionic. Okay, this thing is really a strong bond. Very, very tough to break. Okay? On to molecular solids. Now, again, what are we talking about? We're talking about a molecule. What does that mean? A molecule means it's covalently bonded, right? So we have covalently bonded things that are solid, which is pretty unique if you think about the fact that most of the solids we've been talking about are ionic solids, salts, and then of course we also have metals. But there are some molecules that that are molecular solids. And like all covalently bonded things, it depends on the dipole moment, right? How strong those bonds are going to be, and it is also going to depend on some LD forces. So you've got the dipole moment, the LD forces, and the larger molecules, okay, can bond together. Why? Because they will get a little more polarizable with their LD forces because there's so many electrons involved. So now those with dipoles, those are stronger forces than the London dispersion, and then of course hydrogen bonding is stronger than a dipole force. And then the important thing is to remember, and I focused on this quite a bit last time, no matter how strong the intermolecular forces are, it's much weaker than the forces in the bonds, which, as you remember from the start of this chapter, are the intra. Those are the bonds that hold together an ionic bond or a covalent bond. And then this is hopefully intuitive to you by now. If you have stronger forces, whether it's a covalent bond or an ionic bond, that leads to higher melting and higher freezing point. And the reason being is the only way these are going to happen is if you have is if you can overcome those intermolecular forces. All right? So that's molecular solids. Let's move on to the ionic solids. And these are our salts. And the forces that are, the dipole forces are extreme. If you think about it, you've got a positive charge attracting a negative charge. Those are very, very strong forces. And so those cause huge melting points and huge boiling points. Imagine yourself trying to melt salt. Put it on a pan, dump some salt in the pan, and see if you can melt it. On a burner at home, it's unlikely that you will be able to melt it, right? Now, if you have an ionic solid, those are locked in a lattice, and you guys have all seen the model in my classroom. They're locked in the lattice, so they're easily breakable, and they're probably the easiest way for me to draw that is something like this. Imagine these charges like this. Imagine this is a big crystal, right? If I were to just bump it right here, that would cause this to go down, right? Now a negative charge would be next to a negative charge, and that, of course, would cause it to break. So ionic solids are very brittle because you just got to move those ions just a little bit, and now all of a sudden a similar charge is next to a similar charge, and that's going to cause it to break. And then, since all the electrons are accounted for, in other words, they're locked in, okay? They're locked in. Since they're locked in, ionic solids are not good conductors, which means they're good insulators. They don't allow conduction of electricity. Now, hopefully, those of you remember when are ionic compounds good conductors, and that is, of course, when they are either melted or dissolved in water. All right, so let's got a little question for you here. What type of solid will each substance form? So if you want to pause the video here and just review over what type of solid, whether it's an ionic solid, a molecular solid, an atomic solid, that kind of thing, write that out, and then I'll write it out with you in just a second. All right, so diamond, as I mentioned before, that's carbon. So that's a network, covalent network. This is a molecular solid. Molecular. Okay. This is an atomic solid. This is metallic, right? That's just good old magnesium. This is an ionic solid. Sulfur and fluorine, molecular. Quartz. Now, what is quartz? Quartz is silicon oxide or silicon dioxide. So that is a covalent network solid. Again, these two right here, whoa, super, super strong. Here, this is ammonium nitrate, right? Ionic. Which one's that? That's just an element, right? Argon? Is argon in the metal? No. Okay, so that must just be an atomic. Copper, metallic. You can also put atomic, right? And I guess I should have put atomic over here too. And then this is a molecular solid. All right. So there you have it. We'll talk about this a little more in class, and if you have any questions, don't hesitate to ask. See you next time.